Testing. All right. How's it going? My name is Brandon Fairchild. I'll be showing you my xfoil project. So what you're going to want to do first, or what I did first, was went online, found all the coordinates for Clark W airfoil, and then I just copied that over to a notepad. um, and once you copy it over to the notepad, so let's see if I have it. Okay, so nope. Well, anyway, you have to make sure it's in the right format, and you want the format to be from the top lead or trailing edge. And you basically want to go in a counterclockwise direction around the whole airfoil. So working back from the top leading edge or trailing edge to the leading end, which goes up to here, and then from the bottom leading end to the trailing end. And that's the format that it should be in. So what I had to do was reformat the top part. So just basically invert it in Excel to get this, and then you save it as a data file. So when you're saving it, just save it as a data file and make sure it's in the proper file. So basically I had mine saved to my xfoil folder so that it makes it easier to load it. So here we're actually loading Excel, or xfoil, sorry. Let me clear everything out in the background just to make it easier to look at. Okay. So the first example I will show is just an airfoil with no flaps, and just how I modeled that. So first you're going to want to type in NACA, type in the foil number. So this one, as an example, we use 2415. We're going to want to use pane, which is going to make it basically smoother, easier for the program to computate around that airfoil. PPAR is going to display it. And now you'll see sometimes it doesn't display correctly. When that happens, you just want to type in that again, PPAR, and now it's showing correctly. Next, let me just make sure this is recording actually. Okay, so the next step you want to do, I'm just going to close that. All right. So after that, the next step we're going to do is to add some parameters to it. So the number of nodes I could type in as N250, or you can see if I just type in N, then it will be enter number of panel nodes, type in 250. Then we're going to type in T1. That's pretty much about it there. We're going to go over to the operations. So just OPER. Enter that. We want, if you don't enter any type of Reynolds number, it's just going to calculate for an inviscid flow. So I'm just going to show you a viscid flow. Let me type in Opper again, then Visc. Sorry, Opper, Visc. Enter Reynolds number. Let's say for this case, we're going to enter 3 million. Enter. We also want the number of iterations it runs. It's automatically default to 10. Let's set it to 100. And you can see here, the number of nodes has increased, especially around the leading and trailing edges. So the next thing we want to do, we could just mess around here, and we could set our alpha to 0. That's just our angle of attack. So up here, you could see the pressure coefficient chart, and then you could see the actual foil and how the air flows around. So you could see right here we have a little bit of separation towards the trailing edge. We can reformat this data in other ways if we want, or test it with different angles of attack. So if I want to type in alpha 5, we'll calculate it to that. In this project, we did have to do between an alpha of -5 to 15. So the way we would do that is ASEQ, or alpha sequential. And you could just type that in, or you could type out you want it from -5 degrees to 15 degrees with 1 degree iterations. But let me show you what it looks like without that. So enter the first value. It's going to be -5. the next value is going to be 15 with increments of 1 degrees. So it's going to calculate that, and you'll see it start popping up on the chart over here. So we'll just wait for that to finish loading. All right. From there, we pretty much got what we're looking for. We could also display that differently, typing in sequential P. So next time that I do plot this, so let me just plot this again. You can see that the plot layout changes. But for some reason it doesn't like to pop up here. I don't know if it's just my computer or the program, but it's not loading in there. From there, the next step we could do is write that to a file. So to do that, I'm going to type in PACC to enable what I'm going to write to the file. Then you just want to name it. So I'm going to just do test. But this is what you were going to type in to save it to a file, so name it accordingly. Hit enter again, and then we're just going to run what we wanted to write to the file. So I wanted to run -5 to 15 to 1. So from -5 degrees to 15 degrees with 1 degree increment. Hit enter. It's just going to run that. Oh, and you can see on the left side it is working now, so that's what the graph will look like. All right, and then just to finish writing it or disable what it's writing to the file, you're just going to type in PACC again, and you'll see that it says polar accumulation disabled. So from there, let me just open a blank Excel. All right, let's open. And then you're just going to want to navigate to that file. So let me see if I can find where I saved that to. So here are all my files. If it's not showing up, just go to all files and have it display all files because it is not an Excel file. This one I named test, so I'm just going to open that. And to get it to format correctly, you want to set it to fixed width, and that's just going to sort out the all the information to different cells and columns for you. And then we could just hit finish. So now you could see everything loaded in here, and it will display your lift coefficient, drag coefficient, and all of the other data that it outputs. And it will give you the angle of attack, and then from here we could graph. So I could show that really quick actually. So insert graph. The scatter plot generally works best. Let me make sure I have nothing selected there. And then we could select data. And so, for example, we had to plot, this is for 15, we had to plot alpha versus CL or lift coefficient. So our X value is just going to be our angle of attack, hit enter. And our Y value is going to be our coefficient of lift, which I did not select that properly. All right, so there would be our plot. I'm not going to add labels or anything, just to save on time. But essentially, I did this for the Clark one, for the 2415 airfoil, and for the what was it 0015 airfoil, and then plotted all of those together so we could see that. I think I put it here. So I just put all the data and put it all into one graph. Anyway, moving on. That's one step to doing it. Let me show you how you would read. If you could either close it or just type in quit and it will close it out. Let me open another one. Oh, do I have two open? Open another one and let me show you how to load a file. So all you'll do is type in load and then the name of the file. So type in whatever you saved it as, and that's what's going to load it. And you'll see that it says plain airfoil file. That will just show that it loaded it properly. Otherwise, you'll get error messages, wrong file name, or file cannot be found, something like that. From here, we would do similar steps as we did to the first airfoil, but now I'm going to show you what I would do to enter a flap into the situation. So first, we want to enter the foil name. So I'm just going to type in test foil. It should pop up there. If not, just type in PPAR, and that's what's going to get it to display. And then you can see here, it gives you a warning message, poor input coordinate distribution, excessive panel angle. And then if we just type in pane, it will repanel it for us. So that just works better in the program. So first, what I'm going to start out by doing is set ppar, enter the number of iterations to 250. So if you take a look before I do enter this, you could see the number of nodes on here are kind of sparse. So doing this, if I hit enter, and then T1, it's going to increase the number of nodes over here. Okay, next, what we want to do is GDES. This is going to allow us to add flaps into it. As you can see, you are working with a buffer airfoil. So we're going to type in flap, enter flap hinge location. For the X direction, we're going to just add in 0.7, enter flap hinge Y location or 999 to specify it more accurately, which I'm going to do. And that's going to be set to 0.5. And then the flap deflection in degrees, I'll set that to 15 since that is one of the degree angles we used in the project. 15. All right, so now you can see we added a flap into it, and you can see it comes down towards the back there. Next, we'll just get, we're going to hit EXEC for execute. Let me just mute this, sorry about that. Hit enter, and that's just going to save it into the system. Next, operation or oper, because we want to add in, and we could do inviscid flow by just skipping the viscous step, but we want viscous flow on this one. You would type the according Reynolds number. In this case, let's stick with 3 million, and, just for the sake of the project. We want the iterations to be 100. So for here, we pretty much have everything set, and we can start running our calculation. So if we wanted an angle of attack of 0, it's going to calculate that and show our distribution. I must have typed something in there wrong because it's not displaying properly. Okay, I'm just going to keep iterating this, see if it converges. Okay, for some reason that's not converging. But essentially you would type in the same commands I did as the last airfoil that I worked on, and then write it to a file, and then from there it would be good. And you can see down here, you can see how it flows over the flap with the separation here. That's about all of what we used for the project, or what needed to be used for the project. I could run through it one more time just so it shows it converging. So let me restart this and do it one more time for you guys. So loading this up, I'll just do it on a standard airfoil, not one that I uploaded. So NACA 2415. We want to paint it, ppar to display it. Let's set the number to 250, T to 1. Next, we want to add a flap, so GDES. Oops. Sometimes when that happens, you want to just hit enter a few times until you're working on the xfoil itself, or the airfoil. So here we'll type in GDES, hit flap, and then we're going to enter the same location as we did, so 0.7. 999, so we could specify y over t, which is 0.5 with the angle degree downwards of 15. If you wanted an upward flap, you would have to do negative. It'll do it opposite. Execute that. All right. And then finally, we're going to do opper, add the viscosity, which we want a Reynolds number of 3 million with 100 iterations. All right, and then we could test it out. So alpha, let's say starting at 0, that's going to run, and we should see it start popping up there. Yep, there it goes. Again, I'm running into the not converging. So I must be doing something wrong. I did have to run through the project quite a few times until it came out correctly. Let me see something. -5, 15 iterations of 1. Let's see if this works out properly. Okay, there we go. That's what we're looking for. Nope, that's still not converging. Never mind. Anyway, those are all the steps I did take to finish this project. I'm sorry it wasn't working for this example, but you could see I've outputted all my values and copied them over to the same Excel sheet. So we have like the Clark W with the 25-degree flap and so on. All right, well, that's about it for today. Thank you for watching. Hope you have a good rest of your day.